G'day everyone and welcome back to my channel. I've been away the last few days. I've had quite a few problems. I've had a terrible toothache for 2 days, so I couldn't talk. Yes, I have to go to a dentist and get work done on my teeth. I'm saving up for that at the moment actually before I buy more equipment. Um, and then I've been sick on top of that, which didn't really affect me too much because the cold was already basically going away when the tooth pain started. And then lo and behold, yesterday, I don't know what happened to me again, but I gotta say, because this happened to me literally a few weeks ago, I bought components from China that were all just mixed floor sweepings. And I started sorting them out and I got really sick. Well, guess what? I shit you not, it happened again. Because I had a cold and the cold was getting better. I was getting better, I was fine. I mean, I didn't even get a cough. I got a sore throat, a bit of a runny nose, and then the runny nose cleared up within a few days, and that was it. Anyway, I start sorting these components out, and the same thing happened to me last time. Started feeling really sick, but this time it got even worse. I ended up with this full-on fever, sweating. I felt like I was about to vomit. Like I was really sick. I was shivering, caught up in a ball in front of an oil heater. I don't know if everyone out there knows what an oil heater is. I imagine most people would, but it's not a filament-based heater like nichrome wire coiled up in some sort of former or silicon crystal, what do you call it, quartz tube or something like that. It's basically metal columns with a heating element in the bottom of it and sometimes in the top on some of them, I think. I think they're just in the bottom actually. But anyway, it's filled with oil and the oil circulates around, because heat rises. And they throw off a lot of heat, like a lot. They run at 2400 watts and you can literally crank them up all the way and they'll just stay on. So if you could imagine a huge thing that's like, it's a meter long, running at 2400 watts with all of its thermal mass of the oil, the heat that comes out of these things is insane. And I was sitting in front of that and I was still cold. So I don't know what happened. I woke up this morning, bloody perfect. 1 day fever. So I don't know what to make of these components, but that's the second time I've got floor sweepings for like $15 or $24 for this huge bag of just random mixed components from China. Don't know where, but just some factories over there. And when I sorted through the components, I've gotten really sick, and I never get sick. So, I mean, I know a lot of you are probably going, oh, this sounds like a bit of a conspiracy theory, Dave. Something you'll come to realize after, I don't know, it might take a few years before you pick up on it, but I never get sick. So, like I get a cold, like I said, it's gone in a couple of days. I just had one, as you can see, it's gone. I've probably had the flu 3 times in my entire life. I literally got it once or twice when I was a kid. No, and then I've had it twice as an adult. Once when I was once when I was a teenager, and sometime in my late 20s. And I'm 33 in 3 days, and still haven't had another one yet. So I find it really, really odd. I hate to be one of those people, but I feel like, I don't know if it's COVID or if it's just some sort of flu or just some other bug, but that is 2 times that I have sorted through components that literally came from random factory floors that were swept up and sorted them out and then ended up feeling sick. And they are all dirty and dusty and stuff, so it's weird. Anyway, that's not what this video is about, but I just wanted to let you all know why I've been away for the last few days, because I've actually been meaning to make videos. And as you can see, in the meantime, it's not just this, I've got other stuff to show you. I've done some work. So I've done all my preparation work over the last few days, even though I was sick. Yesterday was the only day I got nothing done because I was literally effed. I couldn't do anything. I was freezing, just curled up in a ball. But the other days that I just had a runny nose and sore throat and all that, I sat around and worked out what I was going to do. And that's what we're going to talk about now. So, Um, I've actually done quite a bit of research because I had time, right? And I'm the sort of person that I hate. If I'm not feeling well, I'll sit around initially, and then after a few hours, I just get the shits, and I have to go and do something, even though I'm sick. And so I ended up just doing a whole ton of research, taking notes, and getting components and just getting everything ready for what I'm about to do. So a few people have bought this and they're actually happy with the performance of it, which is really good because that I could already tell looking at the chip um, that it's a genuine chip. And like I said, I'm pretty new to the RF world, but I'm not. I've watched tons of videos from different channels, people from CB radio, people, building people, to like Inside Guy. I've done my own research. I'm not someone that's physically had a lot of hands on it, but obviously I'm an electronics expert. So it's when you're already in a field or something and you watch videos on something else that's still related to your field, it's basically the same as doing it yourself because you understand everything that's going on in the video. So you are learning, right? Maybe if you're watching it as an outsider that doesn't already have an understanding of electronics, then yeah, fair enough. You're going to need to play with it yourself. But I'm starting to get a pretty good understanding of stuff up in the frequency range, which is good. So what I've decided to do, seeing as this module's good, but I've already done all the math on this and it's not going to be the most useful project, but I decided what we're going to do. Actually, before I explain my logic as to why I'm going to do it in this order, what I'm going to do is I'm just going to show you. Do I not have the image locked? My apologies. Now it won't let me lock. Okay. Okay, so I'm going to buy this. It's 21 bucks. It's 81.29. It's got a gain of 10. It's just set like that. If you short the feedback pin to the output, it's already got a gain of 10. This one, when you short the feedback pin to the output, it's got a gain of 1. So I'm going to get this board too. It's already dual supply, as you can see, which is good. So I'm going to do a test on this as it is. But we'll go into this in a minute as to why I'm going to build this one, then this one, and then redesign this one. I just wanted to show you. Also, I've got a few things up here to get through. Well, one thing at a time. All right, so what I had worked out, okay, most of this was already on here the other day. So with the 8130, the one I've got at the moment, what I've decided to do with it, it's got a 12.5 nanovolt per root hertz noise floor. So what I've decided to do is I've done some measurements. You know what? Just screw these pages for now. Well, actually, when I get the AD8129, I'm going to put a 200 megahertz bandpass filter on it at the -3 dB point. That'll give 63.64 microvolts RMS. That'll give it also usable bandwidth up to about 20 megahertz. Obviously, it's going to be missing harmonics, so you're not going to be able to look at square waves through it, but you'll still get your peak to peak. You'll be able to measure noise accurately. So that's great. This one, if I put the 8130 with the 12.5 nanovolt per root hertz noise floor, it would work out to 176.78 microvolts. Like I said, this is just my own notes. I just said that anyway. Now, the PCB that I've got, not this is for another project. It's for all these 3 projects. This PCB, not this PCB. This isn't even fiberglass. This is phenolic. That's why this is for something else. This is the FR4. I've got its exact measurements. The FR4 is 1.575 mil thick. The copper's 0.035, 0.035 on the other side. The total's 1.645, copper, and FR4. The dielectric constant of this board at 20 megahertz is going to be about 4.3. I have one more thing to calculate, and that's the effective trace width. Sorry, I should not have said that word. I just said something really stupid. Effective signal width. That's what I meant to say. I had to look at the PCB calculator to think about what I was saying. Anyway, I am going to do it by hand. I'm going to etch the board. But it's a double-sided board I chose. So what I'm going to do is the exact same thing as this. I'm going to use, well, let's look at this. I'm going to use a PCB calculator so that I can calculate the microstrip channels that need to be controlled impedance. All right. And then I'm going to do the same as what you do. You see all these little via holes that neatly go around all the stuff that needs to be shielded, guarded. So that's what we're going to do. We're going to calculate the trace widths, the spacing between the via holes, all that stuff on the PCB calculator. And then I'm going to actually etch this up myself, drill the holes, put, whether I flood them with solder or I put little bits of wire or something through the holes to connect the two, to stitch the ground plane to the ground bits on the top. That's what we're going to do for the board. So we're going to spin the boards ourselves, not through. I was tossing up whether to do like JLC PCB or do it myself, but honestly, this is so simple. And I really enjoy doing this anyway. And I also want to prove that it can be done because I've done a lot of research over the last few days, and the frequencies I'm using with proper layout, even with through-hole components, we'll get to this in a minute. These capacitors are these are very good quality ones. These aren't those cheap Chinese ones. Have a look. See? These are proper NPO 1 picofarad capacitors. High tolerance. These are good capacitors. Anyway. I forgot what I was saying. The NPO or COG. I think the NPO. Yeah, the NPOs. C0G, sorry. Anyway. Yes, right. So we're going to analyze. Well, hold on. Let's just go back to what I was saying. I've done a bit of research and I've worked out, like with my 1 meg. Sorry, I haven't shown you the schematic diagram yet. Let's just say I've done my research on component selection. These capacitors, because I need 1.5 microfarads. Picofarads. So we're just going to put 2 of these in series and put that in parallel with the 1 to give us our 1.5. And, if you do this neatly and stack them up tight, that'll fit in between a couple of ground traces and it'll be fine. I am going to order the correct capacitor. So this is just temporary anyway, but it'll allow us to get a start on. Obviously, I'm not going to order that style capacitor. That's got ridiculously high ESR, and I want lowest ESR possible for this. Like I said, this is literally just to get us started. However, that's for the bandpass filter that goes in the feedback path. So it's going to work better than what it would work if you're using it as one of the input or output capacitors, especially the output capacitor because of the high ESR. All right, so you're probably going, all right, what are you talking about? What are you talking about? Okay, so before I get to what I'm talking about with this, because I've got to show you the diagram, what I've come up with, we're going to talk about this battery box. And you can kind of forget some of what's on here because I've been working. No, it's going to be 6. And we're going to have all right, so I have 3 amplifier projects, right? This one, the one that I've just showed you I'm going to buy, and the T100, which is a low noise amplifier that's got a switching power supply that couples 70 millivolts peak to peak noise onto the negative rail, which is just bonkers. I have 2 of these boxes in my lab that I bought a while ago. I was going to build a super low distortions signal generator for audio analysis and buy like a Keithley 2015 THD multimeter and have that, the FFT on my scope and the signal gen and be able to do rudimentary analysis. Then I discovered the Quantasylum, so that's not happening now. Well, actually, I don't know. I haven't looked into this if the Quantasylum actually sources signals. I'd imagine it does. I mean, if it doesn't, then we're still building a signal gen. I've come across a project for a signal gen that uses some insanely expensive parts, but I'll have to get the thing up to show you, because you wouldn't believe me if I told you what the noise rejection and everything is on it. It's insane. It's probably one of the best in the world. No, it's not some lamp stabilized Wien bridge oscillator or something like that. No, it's way past that. It'll blow your mind when you see it. Some of you might already know what I'm talking about. It just depends if you've been around. Anyway, so I've got these 2 boxes. I've still got the other one. I've just opened this one and I've decided, well, I want a battery box. Let's make a super low noise supply, battery based. For now, actually I need to go grab 2 more of these clips and another 2 batteries. I'll do that in a minute. Because what we're going to do is, and I'll just get up a picture that I stole off of Google just to show you guys, because I'm literally too lazy to draw this just to show you. But what I've decided to do is to take 2 7905s, flipped, so this circuit upside down with the center rail connected. You might already get where I'm going with this. What that will allow me to do, one switch for the 2 batteries coming in, the 2 battery feeds coming in to turn it on and off, the whole unit. And another switch, the outputs will go to the middle 2. These 2 will go to the filtered output of the 5-watt regulator, plus and minus, and these 2 will go to the 10. So we're going to build a battery box that's going to have, plus 5 or plus 10, minus 5 or minus 10, and 0 in the middle, that's switchable. 2 voltages. Couple 7905s, couple 7805s, couple 100 mic at 16 volt, couple 100 mic at 16 volt, that's for the 4 outputs, and 400 nanofarad capacitors for the 4 outputs. Don't ask me what I was thinking there. Let me go get another 2 diodes. Obviously I need 4 diodes. Because this is battery supply, you're going to have capacitance on the output, plus whatever your load is attached to it could have capacitance as well. So you're going to need diodes across the regulators, so when you turn it off and the battery voltage is disconnected from the input pin, you don't have voltage on the output pin, making the emitter base. Yeah, thank you. It's got delivery. Yes, thank you. You didn't hear me. I forgot what I was saying. You don't want to reverse bias the emitter base junction of the series pass element in these guys, because you'll break it. So 4 diodes, 4 007s will do. I got a LED and a little insert thing and a 680 ohm resistor. The LED is going to run across the 10 volt rails. The reason for this is because I don't really want to put a load on it, and these regulators are pretty well stable without a load, but I'd like a very small load, even if it's just 5-10 milliamps, a couple milliamps even. Probably will be closer to 5 milliamps or something like that, I don't know. But I figured the 2 5-volt regulators feed another 2 5-volt regulators, so if you load the 10 volts down, you've got a load across all 4 regulators. So I can just put the LED, the power status LED. And I've actually chosen the resistor value at 10 volts with this particular LED's forward voltage so that it goes bright enough that I'm not going to leave it switched on because it's too dim to notice it, but it's also not that bright that it's just burning away battery power, because this is going to be battery based. So that's what's going on here. So that's what this box is for. We're going to have a battery supply so that we've got, you know, a super low noise output, you know, microvolts or less, and we can use that to run this amplifier, the next one, and this one. And then I don't have to build 3 power supplies for these. I'll have a dedicated little box on my bench, right? That's the front. Sorry, that's the back, I think. Okay, they're the same. Yeah, so I'll have a dedicated little box on my bench, and I'll be able to, and this will come in handy for so many other projects in the future, because a lot of the time you need an isolated supply that's completely floating. I don't even mean just a transformer, I mean like completely floating. Because you still got interwinding capacitive coupling and, you know what I'm trying to say, there's all sorts of coupling going on in a transformer. It's not really isolated. A lot of the time you need a battery supply, and you need something that can put out less than microvolts of noise. And if you're wondering why I chose to go this route instead of 337s and 317s, 337s and 317s are not actually spec'd exactly the same as each other. And in the noise department, the 337 is noisier than the 317. Now, I know this is being run from battery, so that's neither here nor there, but yeah, I'm just a perfectionist. Plus, this way is just a nice, easy way of getting that switch on the front to go between 5 and 10 volts. It just works, you know, like it's the simplest, nicest way of doing it that I could think of, you know, and you could actually pull a bit of power out of it too if you needed to use it as a power supply just for some weird reason. Having 2 regulators in series means that the heat's going to get dissipated across the 2. The battery voltage is only going to be, say, 18 volts. 4, 8, 12. It'll be 12.6 when it's on lithium ion. I might even make it 16.8. I think, yeah, that's what we'll do. We'll change that to 8. We'll put 8 lithium ion cells in there. So, you know, 4, 8, 12, 16.8 for each rail. 16.8 volts to run the 2 regulators in series. That gives plenty of headroom, so it's going to run for a while and be able to discharge the batteries good. And, you know, you'll be able to get a little bit of current out of them too, if you need to. So I just thought it was a no-brainer, and the beauty of it is because it's running on batteries, as you load it down, it's not like the input ripple is going to go up. So, you know, this is going to be a good performer as both a power supply and a little low noise power supply for all these amplifier projects and other things that will require that sort of a power supply. So anyway, enough waffling on about the power supply. That's why I've decided to do that. The next thing I wanted to talk about, or should I say do, is we're going to hook this up to the power supply and the scope and the ARB. Now, because, I need to show you what I've actually done. Yeah, I screwed up. I did the stupidest crap here twice. I basically drew the capacitors in series with the power, and then I realized what I did, and I had a laugh, and I couldn't be bothered redrawing it, so I just cut it out. But it makes sense to you guys. AC coupled inputs. These are already insanely high impedance inputs. Output 1 meg resistor, because you can think of this as like a 0 ohm. It's got extremely low output impedance. When I show you the block diagram of this on the schematic, it'll make sense why I can do this, and also why this here isn't going to affect the impedance here. PD pin, power down pin just goes 10k to ground. You've got our +5, +10 volts, -5, -10 volts, whatever it's running off. 10 microfarad decoupling caps to ground and 100 nanofarad decoupling caps to ground. And then here we've got a 1k resistor, and if we put 0.78 0.78 picofarads. It will have a 200 megahertz filter, 1.5 picofarads, 100, 1 picofarad, 160. I chose the 1.5 for 100 megahertz in the end because that will give us 125 volts. God, can you imagine 125 volts of noise? 125 microvolts of noise RMS, and it will still be flat to 10 meg. Most power supply measurements until recently was still only done in the 7 to 8 megahertz bandwidth. You'd be surprised. Go look at some older Keithley data sheets and stuff like that. You'll see what I'm saying. So this is still good for the first project. And the second one, because the second one has a lower noise floor, we went over this before, but just again, the 808129 I've got to buy is what I'm talking about. Because that's got an even lower noise floor, it works out to be filtered at 200 megahertz, only 63 microvolts RMS. I'll be happy with that for that amplifier. I'll be happy with that for both of these, what I've just shown you. This one will obviously be quieter again and have more gain and all bells and whistles added to it. That's why I want to do these two first to get a feel for this sort of thing and get good at it before I do that one. And like I said, we'll have a battery box to power all these things and future projects. So that's what we're doing. I'm just going to take you back to the computer now. I'm just going to show you. Nope. Here we are. So this will make sense in a second. I can find the internal block diagram. Here it is. So it's kind of like an instrumentation amplifier. So it doesn't really matter what you do to this resistor here or the feedback resistor. It's not going to affect your input impedance here, which is why I can build that filter there. I still have my gain of 1. This resistor has to be 0 ohms to obtain that, but I can put a filter in here and it's not going to mess up the ratio. So that's that. That's all I wanted to say in terms of walking you guys through what I've prepared. I've also done some other things too. I've done some research. So, well, the only thing I need to research was my ARP because I didn't have any idea on what the rise and fall time was on it. It's 15 nanoseconds and 16 nanoseconds. I can't remember which one's which. One's the rise time, one's the fall time. You might as well think of it as the same when it's that fucking slow. There I go again. Shit, I've got to stop swearing. Anyway, the other thing to bear in mind, I'm sure everyone knows this already, my scope's only 100 megahertz. I am going to get a 1 gig scope eventually, but, you know, that's not right now. So don't expect to see perfect square wave at 10 megahertz. Because what I want to do now is I want to test this thing at 10 megahertz and 1 megahertz and 100 kilohertz. And I want to take note of the time base and volts per division. Oh, well, that's not going to change. The time base, I want to take note of the time base and the wave shape. I want to load it down, 50 ohm load, because at the moment it's just a capacitor on the output of that. I just can't see that. And this has got a really low impedance output. We'll see when we use it, but it's probably going to need to be loaded down. In my design, I've decided to put a 1 meg resistor on its output so that I can match the impedance to a bit of coax to my 1 meg scope input. But for now, with that board, just as it is, we'll probably just use a 50 ohm load on a T, or actually I've got 50 ohm pass-through boxes that I built myself, so I've got plenty of 50 ohm loads. So that's what we're going to do. We're going to analyze it as it is, and then I'll upload this video, and then I'll get to work building everything. I'm going to build the battery box first, obvious reasons, not because it's the low-hanging fruit, because how can I power everything else without the power source? So I'm going to do that first, upload that video, and then design this PCB. I've already got all of my component values and everything decided, so it's literally just layout now. I literally just have to calculate the controlled impedance tracers and come up with a nice ground plane on each side and stitch it together and etch it. Well, that's the wrong order. Etch it and stitch it together. You know what I mean. But yeah. So it'll be this video, battery box video, and then the amp build video, and then I guess we'll do some evaluation video where we start evaluating the performance of everything, including the battery box, because I'll be curious to see. I don't even think until I get this thing properly built that we'll be able to see the noise coming out the battery box, because my scope can't really see anything lower than, I mean, like if you really mess around with coax being as short as possible and shielding everything, or yeah, like basically measuring something straight off the input, you can get down to about 40-50 microvolts noise floor on my scope. So I mean, with the inputs unplugged, sometimes it's around 30-40 microvolts, but that's pretty useless. So it's going to be harder to see anything under roughly about 50 microvolts, 40 microvolts on the scope. So anyway, I'm now going to set up, I'm just going to power this off 5 volts off the power supply, that nice old school one. Set up the SMA connectors to the ARB and the scope, and we'll run some analysis on this. Something I just wanted to point out about the battery box just quickly. What I was saying before, I wasn't too clear. What I meant to say is if you're using 10 volts, right, the power is going to be dissipated across the 2 regulators. Now, you're probably likely when you're using 10 volts to be using more current too, if you're using it as a power supply to power something, like not just a little op amp or something like that. So that kind of works good. Also, as the batteries go flat and the voltage goes down on the input, the 10 volt rail will be even more regulated well, because you will have a regulator referenced off a regulator. Let me just have a look at the schematic. That might not actually be the case. Hold on, because I'm stacking them, aren't I? No, don't restart now. Let me think about this. Let's see. Well, yes, because the second regulators, sorry about that. The second regulator's ground is looking at the stabilized output of the first one. So as this voltage is shrinking, this isn't. So this will have a more stable output, which is handy as your battery is going flatter. And the 5 volt, well, because it's 5 volts and the battery is going to be like 16 volts, there's that much headroom for the battery to shrink before it becomes an issue for this. This is going to work out well, is what I'm trying to say. You know? And like I said, if you're pulling current through here, oh, you know what? No, you're not. You're not passing it through 2. You're only passing it through 1 or the other. Okay, so it works out good for in terms of the battery going flat and good regulation, but you still only got a max of 1 amp really. And I'm not going to be putting heat sinks in here. I mean, I might. I haven't thought about that yet. Let me just go have a look what I've got. Alright, I do have some TO220 heat sinks, but I'm running low and they're all different odd shapes and sizes and colours. Like some black anodized, some just alloy, and slightly different sizes. What I'll do, because I've got to go to J-Car still and get that nibbling tool, my power supply. Whoops. I've got a little video coming up. My power supply is still sitting there, literally just waiting for the panel meter to get popped in. There's nothing wrong with it, it's finished. I literally just need to solder 3 wires and get a nibbling tool and finish cutting out that hole. So when I go to J-Car, I'll pick up some heat sinks for this. I'll grab like 10 TO220 heat sinks, and then I'll have some spares and 4 for these. That way, if I want to use it as a power supply, at least you can pull out like, I don't know, quarter of an amp, half an amp or something without them getting too hot with a little heatsink on them. So that will make it a bit more useful. But for now, I'm not going to put heatsinks on it. For now, it's going to be 9-volt batteries and no heatsinks, and then, I don't know, probably not in a couple of days. I might get the heatsinks in a few days, but I'm not going to just do a video on installing heatsinks. I'll wait until I get the charge module and work out what I'm going to do for batteries, and I'll put the heatsinks and the battery and charge and everything in and make that a video. Alright, on with the rest of the video now. Alright, so I've got everything set up here. This is running off 5 volts off this power supply. Signal gen's here, and it's just going straight into the scope at the moment. Starting at 100 kilohertz. One channel's got to be offset 180 degrees. Okay. So that's what 100 kilohertz looks like. I'm just going to put a 50 ohm load in here. Okay, so that's what it looks like with a 50 ohm load. I'm just going to short over the capacitor, the output capacitor, and see what it looks like. Direct out the op amp into the 50 ohm load without the capacitor. Okay. So that explains that. I suspected this would happen. Alright, let's just go back into here for a moment. Let's go up to a megahertz, 1 megahertz. I've just got to go and align the phase. Oh, that time it actually stayed aligned. How weird. Okay, that's 1 megahertz. Is the time base showing up on the screen? Because I want to... Okay, good. I want to come back to this later for reference. Okay, that's unloaded at 1 megahertz. Let's give it a 50 ohm load. This is a 50 ohm load, yeah, in parallel, not series. Okay, I'm just going to short that capacitor again. Yep. Starting to see the slew rate of the op amp come into play here. Although, probably not. This function generator is got a pretty shitty slew rate on it. Wonder what happens if I short the capacitor going straight into high impedance. Nothing. Okay, alright, I'm going to go up to 10 megahertz now. Alright. Now, I'm going to load it. Hold on, can you get down? Thank you. Again, we'll put 50 ohm load on it. Okay, that looks better. Let me just... What you're seeing there is the limitation of 100 megahertz scope. I mean, I don't know, it should probably look a little bit more square than that, but not much. Because you've got to take into consideration all the harmonics that are missing. 30, 70 megahertz, all that, like the harmonics that are missing from the square wave, so it's going to be rounded anyway. Let's just take a signal out of here, out the amplifier. Let's take this back off, and let's just have a look at it going straight out the signal gen into the scope, just for reference, at 10 megahertz. Yeah, So I would say that's a limitation of the scope. But that's okay. We've now got a baseline. We know what 100 kilohertz and 1 megahertz and 10 megahertz looks like. Loaded, unloaded, going through the amplifier. So I've got my baseline. I have something to compare against after I build the amplifier with the bandpass filter on my new board and all that. Pure supply, blah, blah, blah. I have something to compare against, you know. And just for reference, 10 megahertz unloaded. Versus loaded. So there you go. Actually, there's a bit of a dimple there that's not there when I put it straight in, isn't there? One sec, let me just grab another coax cable so I can just swap this easier. Come here. Yes. Okay, so that's the amplifier. Alright, let's short that capacitor and see if that goes away. One moment. Got too many cables here. Let's short the capacitor on here, on the output, and see if that goes away. And it does. So there you go. So I reckon when I've got no cap on the output and a 1 meg resistor, you know, it'll be nice and matched to the scope input and it'll work good. If it doesn't, I'll redesign it for a 50 ohm system on the output. Either way, we know that we can get this to work nicely with a scope. So that's good. I can impedance match this to the scope really well without even trying. So it's not going to be a problem with that. And we now have a baseline of performance. Alright, well that's all I wanted to do in this video really. I'm going to go off now and start making up the battery box board first, and I'll do a video on that and get it all etched and made up. Probably won't be another video on this for maybe a day or something, because I'll do the whole battery box project first, and I'll do it in probably 1, maybe 2 videos. I might do the circuit board etching video separately so I can put it in the PCB etching playlist, but yeah, I want to get the battery box done first. Like I said before, I've got a few of these amplifier projects to do, and other things in the future will benefit from having it, so it's just a no-brainer to get that ready first. Yeah, alright, well that's all for this video. Now you know what's going on with this. If you got any comments or ideas, leave it down in the comment section. I'd be keen to hear your input. If not, all good. That's all for now, so I'll sign off here and I'll see you on the next one.